the presenter. And we are recording now, so thanks everybody for joining us today in one more session of the Data and AI Virtual Architecture Group. Today, and Microsoft Data Platform MVP, Mr. Edward Pollack, coming live from the United States, and our wonderful moderator as well, another Microsoft MVP from Brazil, Mr. Luan Moreno, is going to be moderating the session once we get going. It's all about columnar data storage today. Deep dive into Parquet, Delta Parquet, Columnstore indexes, and more. We are recording, so you will get this in the YouTube archive in a few days. And also keep in mind, we have more sessions coming up all the way until the 15th of December, I believe, and then we'll take a break for the holidays, and we will be back in mid-January with more sessions as well. So feel free to use the chat if you have questions, though we will likely be holding the questions up until the very end, and then we will go through the questions. All right, so without further ado, thank you, Ed, for joining us today, and the floor is all yours. And everybody else, just remember to stay muted. Bye-bye.
All right. Thanks as always for having me here today. This session is fast-paced. We talk about a lot. I wish I had 4 or 8 hours, but I have one, and one will suffice. The key here is to really show how once you know how one column store platform works, you can begin understanding the rest more and more easily. And so as we go through this, you'll see patterns, you'll see commonalities. This will become easier. And so while I have a massive amount of content that may cause a little brain meltiness today, the goal is that this should end up being simpler and not more complicated as we go through. I will share all the slides and everything afterwards because there is a lot and there's no way it can all be remembered or copied or whatever. So let's dive right on in. This is me. I've been doing the data platform thing for a long time. I really enjoy this. This is fun. Making new presentations with information like this is fun. I love writing about it, reading about it, organizing events, and even sleeping once in a while, though not always. Our goal here today is to really do a super brief review of OLAP, OLTP, and Columnstore, and then really dive a bit into each format. I'm not going to have any demos. I can't go in and demo everything. There simply just isn't time. But in the future, if we get more time, maybe we will. It could be really exciting to dive in each format and look at the files and everything really in detail, but that will not be today. The goal is really to draw commonalities that can be used to improve how we write queries, how we architect data structures, and how we just store data in general to make it more efficient. That's the ultimate goal of all this. Before we wrap up, I take a few breaths and maybe do some Q&A and head out. Most importantly, to start out, it's good to talk about really quick just transactional versus analytic workloads. It's always important to point this out. Transactional workloads are things that have usually people in applications performing transactions, placing orders, bank transactions, times where you have lots of columns of information, but probably not too many rows. And you're really writing the data very heavily. Insert, update, delete, read a few rows, read lots of columns. That's transactional workloads. They tend to be very time sensitive. I want my results back quickly. If I place an order and I click go, I don't want to wait 30 seconds for my order to be placed. My immediate reaction will be that it's broken. I'll use a different site. I'll hit refresh because we all love when people refresh your stuff and it's running. Time sensitive means fast. Maybe lots of text data, things that don't really compress very well. They get very big. Who knows? And generally, we're not aggregating a lot. Transactional data tends not to be aggregated too much. You really want flat data. You might aggregate some, but nobody in a transactional system is saying, hey, take that billion rows over there and give me standard deviation or something like that. If you are, I'm not really sure what kind of transactional system that is, but that would be very uncommon. The flip side of this, and something completely different, is where transactional data typically ends up eventually as you get bigger and bigger, and you have more and more transactional data. Somebody says, I want to analyze that data. And that ends up into an analytic data store instead of transactional. That's a place where you have lots and lots and lots of rows. Typically, the writes are less. You'll insert data, you might delete it, you may occasionally update it, but you don't write it the same way. You're not constantly updating the status of an order 20 times a day. It's a very different sort of data where it may be written once and never again, or very infrequently, or maybe just updated occasionally. Usually require less columns, and the columns tend to be more dimensional and factual in nature, things like dates, numbers, times, stuff like that. And it won't always be time sensitive. And so whereas I click on my order and I want it to process in half a second or I'm mad, here, if you're running a report, or some sort of analytics, waiting a few seconds or longer, it might be okay. It could be even scheduled, who knows? And we very commonly will aggregate. We'll very often say millions and billions of rows. I want sums, mins, maxes, counts, standard deviations, medians, things like that. Very, very common. And you can get far deeper into metrics if you want to, and calculations and stats here. So these are two very distinct workloads. The difference is very important. They really influence how we interact with data in an appropriate fashion, to which, of course, you will then say, well, what about my mixed workloads? I do OLAP on OLTP. What is that like? And the answer is, it may be okay, or it may not be. Typically, it grows organically, right? You build a transactional system. One day, somebody wakes up and says, we need reports on there. And then it goes from there. And a lot of the times, though, your mixed workloads tend to be you have a big table or files or whatever, and 95% of it just sits there and is never changed, and then 5% is being smashed with updates all the time. And so that's typically what mixed workloads look like, and that gives us some flexibility. We can say, hey, let's apply transactional data structures to the current data and analytic data structures to the old data. And therefore, you get some flexibility. Very commonly, we see things like log data or history tables that really are basically just OLAP in nature. Or you may have queue tables using a database as a queue or a database as a stack. Sounds fun, but you're really just creating a very inactive pile of data and a very active sliver. Consider Service Broker or a different queuing service like RabbitMQ or something else. If you're doing queuing, you'll find better performance. In general, though, data is still very repetitive, and depending on how your mixed workload is, it may not all be time sensitive. And so you can just partition between active and inactive, and then apply conventions as needed. In many ways, data lakes are just a mix of OLAP and OLTP. Here's all of your data in one place. You may do some transactional stuff with it, but you're probably just going to do a mountain of OLAP against it, even though it has all the detail. And so realistically, it's analytic data, but it looks a little transactional in nature just because it has all that detail in it. All right, so those are mixed workloads. It's good stuff. I'm going to dive now right into Columnstore indexes and what they look like. We'll then talk about Parquet, Delta Parquet. I'll make some vague references to other things because we probably won't really have a lot of time to go much deeper. Then we can take some questions at the end. Columnstore indexes exist in SQL Server. They exist on other platforms too, like MySQL. Many other platforms have the ability to take a transactional database and throw Columnstore indexes onto them and get the benefits of column-wise storage. In SQL Server, this is how Columnstore indexes are stored. I'm going to kind of walk through different components of it until we have a reasonable picture. I'm not going to go into the nitty-gritty, but I'll give us a lot of information. And so basically, with Columnstore, we no longer store it as row by row by row with all the columns sequentially one after another and so on and so forth. Here we say we want to take each column and store it separately. So first off, we're going to take all your data, however many rows you have, millions, billions, whatever, and group it into row groups. In SQL Server, a row group's 2 to the 20th rows max. It could be less, but it could be that much max. Therefore, if I have 10 million rows, you have approximately 10-ish row groups. You have 100 million rows, about 100-ish row groups approximately. Just to give you an idea of scale, within each row group, we then take each column and compress it separately into what's called a segment. So a segment is up to 2 to the 20th rows of data just for one column, though. So same data type, same values for one column, and that's it. So you have a small sliver of data that's compressed in one place. The beauty of that is that because it's the same data type and just one column's worth of data, it's probably going to be repetitive and compress really, really well. We're going to talk about compression a lot in a second because it's important to everything we talk about here and everything we do. All of this information is stored, like all the rest of the things in SQL Server, in 8 kilobyte pages, in MDF files or NDF files. So like everything else that's not memory optimized, that's where it goes. So no surprises there, stored in the same place as your row-based tables. Cool. That's what a Columnstore index looks like. You have lots of segments. Each segment has its own data type and its own data, just like that. So now, how does it get compressed? I want to spend a little bit of time on compression. Compression is very important. It really influences how we store the data, how we use it, and how tiny it gets. And keep in mind, the smaller your data gets in storage, the smaller it gets when you read it into memory as well. At least in SQL Server, the data stays compressed when you read it to memory. So if you take a 100 gig table and compress it down to 10 gigs, whenever pages are read into memory, they stay compressed in memory. And it's not until SQL Server needs that data for a query processing that it'll then decompress it and use it. So you're saving space all over all the place. It includes backups as well. So each segment is a one column, one data type, one per row group per column. So the total number of segments you have will be the number of columns times the number of row groups. If you have 10 columns and 100 row groups, it's 1,000 segments. And those numbers can get big, and that's okay. In general, ordered data compresses more effectively. I'm going to talk about that a little bit more later. I'm just mentioning it now. If you know anything about compression, you'll understand why. But typically data that is close in proximity to other data, whether it's by type or date or whoever created it, things like that, in terms of probability, has a higher chance of just compressing better, having more similar values. It's a probability game, and it's one where you will always succeed with that assumption. Now we're going to dive right into algorithms. There's no reason to take a break here. Let's dive right into compression algorithms before we talk step back about the rest of column store indexes and how they work. There are many compression algorithms used out there. Some are proprietary, and you can't read about them on the internet very much. Many are just publicly well-known and understood and are used all over the place for many, many kinds of compression. For column store indexes and for Parquet files and for Delta Lake, you'll find that there are very common compression algorithms used across all of them. The simplest form of compression, one of the simplest things you can do, you even get it from just using row compression in SQL Server. Just apply row compression, you get this, is bit packing. Bit packing basically says you've got fixed length data types, for example, an integer. Integers can be 4 bytes, therefore 32 bits, and it's fixed width. So it doesn't matter if your integer is 0 or negative 100 or 65,000, you consume 8 bytes, 32 bits, no matter what. But realistically, you don't need all that space. To represent the value 30, you only really need 6 bits, right? The rest of it is all just leading zeros, and you could really just ignore that if you wanted to. These are some examples of numbers here. You can see how I use 32 bits to store it if you have no compression whatsoever. But the moment you say bit packet, you can now shrink that number down and removing all those leading zeros. And as soon as you do that, you can very quickly shrink the size of numbers or anything represented in numbers a lot. This sample of numbers right here took 288 bits to store the fixed length integers. But if I bit pack them all, then I get down to 108 bits, which is less than half of the size of the original data. And if you're using big int, it's 64 bits, and so on and so forth. So any decimals you have that have monstrously large precision or whatever, bit packing just takes all leading zeros and makes them go poof. And that is valuable. Saves a lot of space, and it's very easy. It's not new tech. This is old. It's been around for a long time. There are many kinds of encoding algorithms out there that take it a step further to adjust how data is represented to either reduce its size or make it more compressible later. They're lossless. All these are lossless, so we're not like compressing like MP3 and losing a little bit of the clarity. We keep everything. The most common algorithms are dictionary, value, and bitmap encoding. I'll talk about all of them, because why not? We have time, right? We have 45 minutes more. We can do that. And the goals ultimately of encoding is to save space, either by immediately saving space or allowing an engine that compresses later on to save more space by handing it data that's packaged up nicely with more repeating bit values, more repeating values. They're just easier to compress. So repetition is the key to compression. It really is from this point forward. The first kind of compression is encoding is dictionary encoding. Dictionary encoding really is just create a hash table of each distinct value in a data set, and then instead of storing the values over and over and over, store an index ID that goes back to that hash value. The larger and larger the values are, like big strings and binary values and things like that, the more you benefit from this. Because very commonly, especially in analytic data, your values repeat. Maybe you have statuses or account names or people names or even like API call information, things that can get kind of long, or browser strings, you name it. There's a million examples of this out there. These can be long. They can take up a lot of space. They could be double length nvarchars or maybe varchars, and they can be big. And so what you do is you convert them into lookups. The real benefit is this: you don't have to repeat your big values over and over. You just replace them with itty-bitty numeric indexes. And of course, they can be bit packed, right? If I replace the value Edward Pollack with the index of 2, well, 2 is just 1 0. It's tiny. It's nothing. It's 2 bits. Done. I replaced a name with a bunch of varchar characters in it with collations and all that garbage, and it's now replaced with 2 bits. So an important note in SQL Server, and you will find this is actually a limitation in many places, SQL Server has a limit on dictionary size of 16 megs. Almost every place that has dictionary encoding, anywhere you go, there's limitations in dictionary size. They can't be infinitely large. Infinity is big, and we can't store data in infinity. I can't, you can't. Life has limitations. Therefore, if you ever find you have trouble where your dictionaries get too big and split, your row groups, that you only have 16 megs of dictionary per row group, consider normalizing some of your giant strings first. You won't benefit from dictionary encoding, but you'll have normalized a problem way. But don't assume this is a problem until it happens. It may or may not be a problem, but if it is, you'll discover it later, and you can research, you can read about it. I've presented on in the past, so there is knowledge out there that can help if dictionary pressure is an issue. We'll assume by default you don't have that problem until you do, because you can't assume in life you have all the problems first. That's just life, right? Dictionary encoding looks like this. I have a table of values here. Desserts, I love baking. So there's desserts here. I just made a beautiful bourbon spiced apple cake yesterday that I can't wait to try later, maybe right after this call. We'll see. But anyway, here's some desserts. There's their size in bytes. If you add them all up, you get 203 bytes, I assume, varchar. So each character is 1 byte. There we go. Now I make a lookup table. I realize, wow, all these values in this table, it could be much bigger than this if we want it to be, just 5 distinct values of desserts. And those 5 distinct values add up to 82 bytes of data, and that's it. My source data has what, like 11, 12 rows there. It could be very much more. If I'm a bakery and I keep all my sales data online, it could be millions, thousands, tens of thousands of the same things over and over, because that bakery doesn't have an infinite menu. It has a menu of maybe 10, 20, 30 things, however many. And therefore, the dictionary will be small and the table will be big. And that's our goal. The more repetition, the better. So now I encode the data using dictionary encoding. And the result's going to be that I now have all my values over there, and they've been reduced down to an index from 0 to 4. I've replaced these ginormous strings that are up to 24 bytes in length. They could have been longer if I had a bigger dessert. And now they're down to 3 bits apiece. And if I bitpack, they get even smaller. So absolutely tiny, tiny, tiny. I went from 203 bytes down to a dictionary of 82 bytes and 33 bits of data. So this is less than splitting the data in half and then some. And if I bitpack the index IDs, it'll get even smaller. So you can combine encoding algorithms. You can combine compression algorithms to get even more savings. So this is very, very common. Even though dictionary encoding probably gives you your biggest benefits on stringy data or binary data, it can occasionally be used for decimals or integers or things, especially big ints. You have like giant numbers. It may just simply, the engine may simply say, we'll dictionary encode it too because it'll save space. Why not? We're already in there compressing. What's a little more compression? The next kind of compression we'll talk about is value encoding. Value encoding. Value encoding is all about using math to make your numbers smaller. We noted back here the numbers that we're talking about are pretty small. They're all zeros, ones, twos, threes, and fours, things like that. But numbers aren't always small. Sometimes they're decimals. Sometimes you have 8 places after the decimal point, things like that. The goal of value encoding is to apply mathematical algorithms to your numbers to make them take up less space. There's many, many ways to do it. I'll introduce a few, but there are many, many more out there that are far more complicated that you can learn about if you're interested. This can be combined with dictionary encoding very, very easily. And as a side note from earlier, when you talk about segments, each segment's compressed differently. Therefore, each one can have its own dictionary. It can have its own value encoding rules and so on and so forth. So every segment within a Columnstore index can be compressed differently with all different values for this kind of stuff. So here's what it looks like. I'm going to say here I have a bunch of values. They're numbers. And there's your minimum size in bits they're going to take up. And then I say, all right, they're all divisible by 10. I'm just going to divide every single one of these by 10. And then my key metric here is 10 to the negative first. And then I'm going to store the values divided by 10 and see how many bits they are. And you'll note that the bit size goes down a little bit. Not a ton, but it went from 108 bits down to 76 bits, all by simply saying divide everything by 10. This is one way to value encode your data with an exponent. I pick it. It doesn't have to be 10 to the negative first. It can be 5 or 2 to the 8th, 10th, whatever. It could be any number. Different algorithms will use different divisors and different exponents depending on the complexity or the sort of data that's in there. But in SQL Server, it's usually going to be using a value like this, and dividing by a single value to an exponent. And you can look this all up, by the way, all in SQL Server. At least I mentioned Columnstore index a lot because the metadata is readily available in dynamic management views. Feel free to look them up. I have other presentations about them. There's lots of documentation on them. But those dynamic management views expose these details, the dictionary details, the value encoding details, which is kind of cool. Here's another example. I can say, hey, let's just take all of our values and baseline them to 0. I'm going to take every single one of my values here and subtract 30. When I do that, they don't shrink a lot in this case. Value encoding like this reduces the size slightly by 7 bits. What is that, like 10% barely, not even really, like 8%. But it does shrink it, and it can be much more useful when all the values have similar values. So this type of value encoding says pick a common base and then subtract it. It could be a negative number, a positive number, doesn't really matter. But the goal is to zero it out and have a value set that has a 0 in the middle and values all around it. This can save a lot of space, or it may not, so it won't necessarily always be used, but it's one way to save space. Here's an example where value encoding like that can save mountains of space. We very often think that identity columns can't compress very well. They're all unique values. Oh my gosh, they're all unique. We can't possibly compress 1 million unique values, can we? And the answer is yes, you can. Identities are consecutive, right? And even if they weren't consecutive and they were close to consecutive, it wouldn't matter. Take an example like this right here, where we're starting at 1.5 billion and incrementing by 1. It doesn't really matter what you increment by. It could be 1, 5, 10. Doesn't matter. I could simply say that my key value is 1.5 billion. Subtract 1.5 billion from every value, and what happens to my values? They shrink down to nothing. So now my values are tiny. Instead of storing 1.5 billion and something, I'm storing the numbers 0 to 9. And so I shrunk my storage from 320 bits down to 46 bits. If you have a big int, you save even more. If you have a decimal like 26.2 or something, you save even more. So the bigger your numbers get, the more this type of value encoding will save you space. And so depending on the type of data you have, one type of value encoding may be chosen over the other, or maybe neither, or maybe both. Those are all valid. You can choose one, the other, or both, and they're all valid. And again, this is mathematical manipulation. It's not meant to be complicated. It's meant to be easy. And you just do it over and over and over whenever it's applicable. If these tables that I'm demoing with right here had millions and billions of rows, your savings would be massive. It's one of the reasons why when people say Columnstore indexes save a lot of space, they mean it, because you really are able to compress many types of data down into just itty-bitty fractions of what they originally were. Here's a type of compression that is really, really important to ultimately getting good compression ratios. When all of our other methods here so far have, whether it's succeeded or failed, this one tends to help a lot because in analytic data, values repeat. It's just how it works. Values repeat. It's very unusual if you had a data set from anywhere where nothing repeated. No account people or names or order ID, nothing repeats. That's weird. So what run length encoding says is, let's find repeated values, repeated byte patterns, repeated anything, and summarize them. And so instead of storing the data row by row by row, we can then say, hey, this value repeats 4 times. Instead of repeating it 4 times, we'll simply say that the value 5 repeats 4 times. Done. So I have a value and I have an index of repetitions. And you can tell immediately this will work really well on sorted data. The data is sorted by that value. You will get really good compression here because it'll simply say, oh, you have a status ID with 5 possible values and 1 billion rows. It's going to compress away into nothing because you have 5 values. They're going to all be the same things over and over. But for something like this, it'll compress well. My example here, data is not sorted. I have 5, 5, 5, 5, 4, 4, 3, 1, 2, 3, 3, 2, 1, not sorted. And so I still save almost 50% on storage with this unsorted pile of random stuff that I made up. But you can save more. So keep that in mind as we talk more about encoding and compression, that ordered data will compress better always. like a universal truth in compression. You want it to be ordered. You want repetition. Those are guaranteed ways to save mountains of space in your data. And any way that you can architect your data structures to encourage data ordering and repetition in your analytic data, the more you'll find that your data compresses from biggie size to little size, which is what you want. Smaller data, bigger data, smaller data. So in SQL Server, Columnstore compression uses two proprietary algorithms. And while they're proprietary and they're patented and all that stuff, you can't learn about the detailed extensiveness of them. There are white papers on them. You can read about them if you have a lot of free time and a lot of coffee, and how they work. So there are two different compression algorithms in SQL Server. The X velocity is used for Columnstore, and Express is used for archive. Archive compression is basically a extra layer of compression on top of the existing compression to make it even smaller. I typically don't use it a lot unless I have cold data, lukewarm data, the kind of data people don't use very much. But it takes more CPU, more resources to compress, but you get more compression, like an additional 10, 20% possibly at most out of it. So archive compression is cool. It gives you more compression, but at the cost of compute when you do the compression. So not everyone uses it, but it's useful if you have data that's not being touched much, data that's there for posterity, or that you don't read very often, or where time sensitivity is not very important. Both of these will always use bit packing, and they will always try to use run length encoding. The other algorithms like dictionary and value encoding will be used situationally if the engine deems it worthwhile. So if it makes sense to use them, it will. If it doesn't, it won't waste the effort and add more complexity to the compression. I mentioned earlier that data order is very important, that row order is very important. When you step back and look at a set of analytic data like this, you realize that within each row group, the row order doesn't matter. This is not like a cluster index on a classic row store table where it enforces data order. In the analytic data stored like this, whether it's here or in Parquet files or anywhere else that you happen to store analytic data, unless you explicitly can specify a data order somewhere, there is no order. And so no order is promised. Therefore, within each row group, order doesn't matter. Therefore, SQL Server can sort the data for you. There's no reason not to. So Vertipaq optimization says that after segments have been encoded and they're getting ready to be finally compressed, before it does all those final compression algorithms, it's going to take those rows of data, now rows, not segments, but the whole rows of data in the row group up to 2 to the 20th, and it's going to sort them. This is expensive. This is not a cheap thing to do. It's an expensive optimization, but it will look at all the values and all the segments, all the metadata about them, and decide what's the best row order that will get the best compression. What will encourage the most run length encoding to take place and shrink your data the most? It's expensive. I mentioned it again, but it's important and it's worth it. You don't want to prevent this from happening. There are some scenarios in SQL Server that will prevent it from happening. I mentioned them here only because it's valuable. One is memory optimized column store indexes. Generally, don't even really want to use those. There's very situational uses for them, but column store does not compress as well memory as it will on disk. So there are very, very edge casey worlds where you may want to do it, but they're rare. Similarly, if you have non-clustered row store indexes on top of your cluster column store, you may have trouble getting all the data to merge in and optimize. You can fix that with rebuilds and things like that, but it's just these little edge cases here where it may not work. You want this, though. This is going to take your data and automatically sort it for maximum compression, and you want that 100%. You'll see a repeated theme of data order throughout this presentation, where data order means better compression. Data order means faster data retrieval, smaller data size, all the good things that you want in your analytic data. Here's an example of Vertipaq optimization. Let's say we have a million rows in a row group, and this is a sample of it. And I have this dictionary encoded data. It's already small. I've already dictionary encoded it away. It's tiny. I only have 5 values, 0 to 4. This data is already pretty small. All I'm going to do here is sort it. So instead of it being 0, 1, 2, 3, 4, 2, 2, whatever, it's now ordered by the index ID 0, 0, 0, 1, 2, 2, 2, 2, 3, 4, 4, done. It's ordered. Now note, this does not save any space. Optimization like this, whether it's Vertipaq optimization or V-order optimization in Parquet or whatever, this is not going to save you any space. It simply reorders your data so that later on you can save space. Metadata is very important to pretty much all column store methods, regardless of what system you're in. Wherever you store your data, if it's stored in a column store format, you need metadata. In SQL Server, metadata is stored centrally about each segment and row group, and this is really important. The metadata tells us things about each segment individually and about each row group. So within each row group, how many rows are there? Things like that. And for each segment, what's the min, what's the max, what's the count? Is it nullable? Things like that. And they aren't like statistics where it's kind of an estimate you got to fix every so often. Here, they're precise. So when you compress your segment, this metadata is created automatically, which means compressing a segment based on all the stuff we talked about so far is expensive. It's important to mention that. You do not, and you do not want to decompress, decompress, make changes, recompress over and over and over. If you do that, life gets expensive and slow. So in general, metadata is very important, and it's created when you compress your data, and it won't get changed until your data gets decompressed, modified, and recompressed, or you create new segments in new row groups with new data. This facilitates row group elimination, segment elimination. Those are the things we're familiar with if you know about Columnstore indexes, and if not, we're going to talk about them shortly. And again, like everything else I mentioned earlier with segments and row groups and all of that and value encoding and dictionary encoding, there are dynamic management views in the SQL Server that give you access to all this information. I highly recommend looking them up. I can post links afterwards if you want to where all the stuff is, but it's just right on Microsoft Learn. It's not secret. It's public information, which is nice. They expose all the underlying information on how they do their stuff, which is good. Understand why things are biggie sized or little sized. Always helpful. Or just satisfy curiosity, because I have curiosity, don't you? This brings me to really important, I made this point a few times. I'm going to make it again, like formally 100% right here. Data order is very, very, very important to compression. This is a game of probability where historically in like all data sets, with the exception of like crazy outliers, data that is ordered by common filter predicates will compress significantly better than unordered data. And you can experiment on this. You could look at data from any data set you have that goes back 5 or 10 years. If you grab the sample of 1 million rows today and compare it to 1 million rows from 10 years ago, the 10 million today has a lot in common. The 10 million from way back when has a lot in common with itself, but to each other, they have less in common. Very often, a date or a datetime dimension will be that dimension that you order by, because a lot of analytics say, give me a daily report, a weekly report, a quarterly report, order by a date time, order by a date, filter by a date, things like that. This may not always be the case, but it will often be the case. And this data order is important. If you throw your data into data structures, analytic data structures, and there's no data order, you just shove it all in anywhere, it will compress more poorly, and you have to read more of it to get what you want out of it. So you're harming yourself in multiple ways. You're making your data bigger and less compressible. And then when I have to go back later and read it and check the metadata to see where my data is, it's going to have to read more data. And so this is a big deal. In the Columnstore index world of the SQL Server, you can rebuild the index to kind of get around this. A lot of people simply say, I'll create a clustered row store, order my data, and then put a column store on top of that with drop existing, and then you get the order you want. Kind of a trick, can take a little bit of time, but it's a nice way to enforce order. There are ordered columns or indexes in 2022. I kind of recommend avoiding them for now, unless you read all the details about them, because they're tricky and iffy and situational, and they don't always work. But hopefully they'll work in a future version. Keep in mind that if you have inactive older data, which in the analytic world is very common, you very often will have the data you write today, or you update this week, this month, this year. But you very well are going to have older data, maybe log data, or old, data warehouse style data, or old data lake data, or whatever, that is inactive, which basically means it's read only. So you created data before today that will never change again. Or if it changes, it'll change infrequently when there's like a software release or a major update or something. If you have old data that's not being changed, you can leave it alone in its perfect order until forever or until it changes. In the world of tables and databases, you can partition them and partition by month or year or whatever to ensure that you have an active partition that's less compressed and more active, where you're adding stuff all the time. You have your older partitions that are more heavily compressed, that have been perfectly ordered and rebuilt, and that are pristine, and that don't have to get touched again. This just makes your maintenance easier. So instead of saying I have 100 billion rows of data and I got to deal with it, I can say, well, of the 100 billion, only 5 billion are recent, so I'll worry about them and ignore the rest. So data order is critical. I'll probably mention it 5 more times today, so don't hold it against me if I do. Data order allows for some cool things, and columns allow you some cool things. You compress your columns separately. Here's what happens. In the world of any column store format, you don't have to read all your data. If I have 6 columns in a table, and I only want to query for columns A and B, I simply pull the segments for columns A and B, and that's it. I can ignore C through F. They're stored separately. I don't need them, so I leave them alone. This means the more columns you have, the more you can save if you don't read them all. So, good tip of advice in analytic data, don't read more columns than you need, because the engine's going to know that I can avoid reading columns I don't need because they're stored separately. It isn't like a row-based table where all the columns are right there. This is a column-wise table, and they're stored separately. Row group elimination is the opposite. This is where I use metadata, and I look for queries where metadata shows that I don't need all the row groups. If your data is ordered by date or something like that, then you can filter by it. So if I have thousands or millions of row groups ordered by date times going back to 2010, and I simply query for last week, I don't need all that data. I only need the row groups that have data for the past week. I can query for that small date range, use metadata to figure out which row groups I need, and then grab what I need. And that's it. This requires ordered data. If your data is not ordered, you may not get a lot. You'll still get some, because data just will happen to fit into filter predicates nicely, but you won't get the same level of beauty that you would get here. If I had 4 row groups and I simply query for a small date range, maybe I only need 1 of them. If I have a million row groups and I query for a small date range, maybe I only need 5 or 10 row groups. That's a big savings, only having to read a tiny fraction of data for the past day, week, month, quarter, as opposed to everything, which is a lot. Combine them. Combine segment and row group. So now I just query for 2 columns and for a small date range, and I go from this example of 24 segments down to 2. That's pretty awesome. I'm only reading a small percent of the data. And as your table gets bigger and wider, this will become more dramatic. If you have 50 columns in a data warehouse table and you have a million row groups because you have a billion rows, and you query for a specific date range and you only want 2 columns aggregated, you'll read a teeny, teeny, tiny fraction of your data, and it'll be fast. And that's the beauty of this kind of compression. Of course, writing is the hard part. Compressing these segments is expensive. Compression algorithms, encoding are expensive. Vertipaq optimization is expensive. All these things are expensive. So to facilitate this, we have things in SQL Server to help. There's a delta store, which will accumulate small trickle changes. If I write a lot of rows, more than 102,400, more than or equal to that, it'll just bulk insert it all in. If I do less, it'll go into a place called the delta store, which is a B-tree heap. Sounds scary, but it's fine. And then it'll asynchronously push that data into the row groups as needed in the background. When you query your data, it'll query the delta store and the Columnstore index compressed segments all together, sum it all up, and give you back what you need. The delta store is generally going to be small. It's not going to be humongous because it will asynchronously push the data over, but it's there to facilitate speedy writes. Because if you're constantly waiting at runtime, for this is an ACID transactional database, if you're waiting at runtime for things to decompress, modify, recompress, you could be here a while, and nobody likes waiting. This facilitates faster data modification. Similarly, there's an object called the delete bitmap. What if I go and delete a billion rows or a million rows or 1,000 rows? Having to go in and open up all those row groups, all those segments, decompress them, delete the rows, and recompress them is painful. You'll wait a long time and your server will cry. So instead of doing that, the delete bitmap is basically just a bitmap of zeros and ones that correspond to the rows and the row groups. It isn't created by default, it's created when you need it. And what it basically says is the following rows are deleted. If you query this thing, ignore them. And so they're not really deleted, they're soft deleted. There are background processes in the newer versions of SQL Server that will come through and clean up the deleted rows for you. You can also force it with some index maintenance, some reorgs and stuff like that. But needless to say, when you delete rows, by default, they're being soft deleted. like this. Again, this facilitates faster writes because you cannot at runtime, when everyone's waiting for their data to load, have everything lock up and wait. You'll break your server, you'll break your users, you'll get phone calls. Nobody wants that. I don't want a 2 a.m. phone call by a CEO to you. No, nobody wants that. So we won't get it. That's Columnstore indexes. I'll just dive back for a second. I went into a lot of detail here because this detail is going to sound familiar from this point going forward. I'm going to talk about Parquet now. Parquet is a completely different file format. It was created by Apache. It's an open source portable format. That's kind of nice. A portable format means you have no vendor lock-in. You can put your data to Parquet files, and if you change platforms in the future, you can simply take your Parquet files, lift them up, and take them with you. You're done. That's really, really nice. Open formats are rare in the world of analytics. A lot of companies might have their own proprietary thing where you get vendor locked in and you can never leave. They love that. But you love this. Parquet, despite being files on storage, is a column-based storage method, just like columns or indexes. There's a lot of similarities, and it's much, much more efficient than other formats. You can store your analytic data in text files, CSVs, XML, JSON, you name it. And many people do. But I promise you, this will not be as fast, anywhere near as fast in those formats because they don't have built-in compression like this. You can compress them, but it won't be built in the way this is. Here's kind of how a Parquet file looks. You basically have a header, you have row groups, and you have a footer with metadata. And as you look at this here, you'll begin seeing similarities, such as row groups and columns within each row group. It's kind of like a segment, right? And you have metadata that tells each one of these Parquet files what's inside of it. What are the addresses for each row group, the way they begin and end, and for each column, what's the path to each one? Because again, if I query my Parquet data, I don't have to read all the Parquet files. I want to just read the ones that I need. So metadata helps for doing that. And you have a footer at the bottom and done. So the format is pretty standard. A column chunk is simply all of the data pages for a column within a row group. It could be more than one chunk of pages. It could stretch and span multiple Parquet files potentially if you have a lot of data. Again, this is as many pages as needed. And so it seems a little looser than a Columnstore index, but it's really the same thing in a different format. And so you can see all the similarities here, which is very, very important. Your row groups will continue sequentially until done. If you have 100 row groups, you'll start at row group 0, and all of your data pages for each column, all those column chunks. And then row group 1, row group 2, all the way up to your last row group. And within each of them, all your column chunks for each column. And just like in Columnstore indexes, they're all compressed separately. Each column chunk is compressed separately. It can compress with different algorithms, just like Columnstore indexes. And yeah, this was developed pseudo-independently of Columnstore indexes, and yet there's a lot of similarities here because the same basic white papers and research projects and university projects resulted in the same research results that resulted in this. So it's very interesting. Here's some notes on the Parquet file format. The metadata is separate from data, and that is very, very important. It provides some optimizations, but not all of them. Because again, these are files on a storage system somewhere. This is not an ACID database. Right now, when we talk about Parquet files, this is not ACID. This is not transactional in nature. If I go in there and write data and you read the same data at the same time, nothing's guaranteed. You may get the data before or after or in the middle. Who the heck knows? So just keep in mind that Parquet files in of themselves are not a database. They don't apply to ACID, atomic, consistent, isolated, durable. They're not transactional in nature. You don't have all those benefits. That's just life. The default data page defaults a meg, and that's fine in SQL Server pages or 8K. You can customize it if you want. You don't have to. In general, I would say accept the defaults until you have a problem and then change it. It's kind of what a best practice is. You accept it and then change it if needed later. It will automatically take your data types and turn them into smaller data types whenever possible. If you have a big int, but everything squeezes into a small int or an int or something else, it will just simply shrink it and squish it and bit pack it into whatever the smallest thing it can. A string isn't a string, it's a binary byte array. Things like that occur. And so it's automatically going to shrink your data type down into the smallest thing that can be easily read to save space. So you benefit from that. You benefit from bit packing and all those things that we talked about earlier, just like Columnstore, which is nice. In SQL Server Columnstore indexes, the minimal unit of reading is the segment. Here it's the column chunk. When we talk about reading, it's column chunks. Can you use Parquet files on premise? That's how the question is going to answer it while I'm here. You can use them anywhere. They're just files. You can create and use them anywhere, but you need a system or an engine to consume them. So, Spark is something people often use, Apache Spark. There are other engines out there that can use it. And for the question about what if you have 100 rows or small data, if you have tiny data sets, you can compress some of these formats. You just won't get a lot out of it. I'm not going to say don't do it, but you don't have to because the impact will be small. These are meant for beauty. If your data is going to grow and get humongous in the future, most certainly do it in this format because it'll get bigger. There are many algorithms provided for Parquet. Spark provides many. These are some of them. You can choose the format that you want to compress in if you want, or go along with defaults. So you have a lot of options here, a lot of customization. Defaults are honestly fine in many environments. If you use this, in Azure or anywhere else, and in Databricks, you'll have all of your options available to you. You can pick them. There's a lot of familiar encoding algorithms used here. I don't know if people are answering your questions. Thank you for everybody for answering questions for me. I appreciate that. That saves me trouble. Run length encoding is used. Dictionary encoding is used. Bit packing is used, just like Columnstore indexes. Nulls are going to be removed automatically the best they can be and minimized to nothing. Columnstore has a very similar algorithm for that. So there's a lot of similarities here, which are really important. Compressions applied at the page level within column chunks. And this is huge. So you get a lot of benefit from compression. You get one more thing here. Something that Parquet files use that Columnstore does not use is delta encoding. There's nothing to do with Delta Lake at all. It's its own encoding algorithm. And basically what it says is take a sequence of values, compute the difference between each consecutive value, and store the delta, and then provide those differences as your stored data. This tends to be good for values that span a small range where you have tons of values and they're distinct in nature. Value encoding can be used too. Other encoding can be used too. But this is one way to do it. And nothing to do with Delta Lake's own model. I'll just show it here. In fact, I'll just show it. Here's an example of delta encoding. Notice that I have a whole bunch of values here. They might be consecutive, but they span a short range from 1,000 to 1,025. And so I compute the delta between each one. From 1,000 to 1,000 is 0. From 1,000 to 1,001 is 1. From 1,001 to 1,003 is 2, and so on and so forth. What you notice now is that I have an initial value, 1,000. I store that. But then now I just store all the deltas. The deltas are tiny. The deltas take up a byte, 2 bytes, a bit, 2 bits, 3 bits. So because of this, I can go from 131 bits down to 20. So delta encoding is a type of encoding that can save a mountain of space. And because Parquet files are read sequentially, they're files, they're not databases, they don't benefit from a lot of the things that SQL Server can give you in a table or Postgres or MySQL or anybody else. Therefore, anything that improves sequential reads in a file will help a lot. And this helps sequential reads in a file a lot. You have to think about this. It's used automatically. But this is an algorithm that can create an immense level of savings. Now, decoding this isn't cheap, though. I have to go through one by one and decompress this and convert my deltas into values, which means if I have the 1,000th value, I've got to go through 999 values to get there. But again, files are read sequentially, so that's okay. Delta Lake, I'm not going to get too much in the nitty-gritty of Delta Lake only because it gets very, very complicated. I had slides originally in here with the details of the files, and then I chuckled and deleted them because it was just too much. It was off the walls crazy. We didn't have time for it. Delta Lake is basically a set of version Parquet files. So it's Parquet, just Parquet, with a whole bunch of stuff on top of it, with a big transaction log. This transaction log provides a lot of things to you that you might want. It allows for concurrent writes. It gives you ACID, transaction compliance. It gives you time travel and versioning. This is a lot of cool stuff. It does cost a lot, though. It consumes more space, it can become fragmented, and if you have a lot of updates and changes, it can get big over time. It's kind of a similar challenge the Columnstore has, the Delta Store, and with delete bitmaps, that as you make changes, they have to go somewhere. And if you want ACID, if you want transactions that are atomic, consistent, isolated, and durable, you got to pay for that a bit. So you're taking basically all those Parquet files and using a transaction log to turn them into something that is transaction-based. And that's a big deal. The metadata is stored in line with the data, just to ensure that your centralized metadata storage can get monstrously huge, because it can be when you're committing changes. Every change is called a commit, not like Git, but it feels a bit like it, where whenever you make an insert, update, or delete to your data, that's a commit, and the transaction log will get noted, and then Parquet data will get created. And all of this information is stored, and it's big. But like Parquet, this is an open data source format. It's an open format, which means that if you have a Delta Lake somewhere, you can just pick up all the Parquet files, all the transaction log files, pick them up and take them with you and go home and put it somewhere else. If you hate your current vendor, maybe AWS stinks and you want Azure or whatever else you have, you can do that. So open format has benefits, huge benefits for portability, no vendor lock-in, or at least less, which is nice. There are many components to Delta Lake. I put this here only to emphasize the complexity of it. This is not simple. You can look at the files and see them, understand how they work, but they're complicated. And so to actually learn them and understand them fully could require precons of information, a whole book to do it. So we're not going to do all that detail here, but I mentioned them here just to point out the complexity of it. So the components of Delta Lake, in addition to your Parquet file, are first the modified data. So what data have you inserted, updated, or deleted? And that goes into a Parquet file. Next, you have deletion vector files. This sounds kind of like the delete bitmap, doesn't it? Because it is. We soft delete rows that are getting deleted because deleting them by decompressing Parquet files and recompressing them is expensive as all heck, so we don't do that. So when you delete stuff, you create a deletion vector file and note which rows are soft deleted. They're stored as binary files, and whenever you read your Parquet files, it'll overlay this and check to see what rows are deleted and ignore them. Change data files manage only changes to data, so updates, deletes, and merges. So when you take your data and modify it, you will create a special Parquet file, and it will contain those changes to understand what has gone from point A to point B. That's for time travel purposes. I need both the before and the changes and the after. It's the only way I can do versioning, is to have all those components in one place. But wait, there's more. You have Delta log entries stored as JSON files. These log all the changes to a table, and they're used for atomicity. So the A in ACID requires a log file. This way, changes are made in atomic chunks. Therefore, until this log entry is made, your changes aren't official. They haven't happened. If I read the data while you're writing to it, this isn't done yet, I see the before. It's versioned. It's kind of like snapshot isolation. It's optimistic concurrency. You benefit from the fact that it's versioned. You have checkpoint files. That's what you really need for replay. If you want to go back and see all the changes to data over time through all the changes that have been made, you need this stuff right here. There's different specifications that have been made over time that make this better. I'm not going to go into the details, but you have it. So checkpoint files can get big, and they're a replay. But if you want the ability to time travel, the ability to do versioning, you just need this. And the last thing that's worth noting here is compaction. I've introduced 5 new kinds of files that are all needed for Delta Lake. And you can use optimize commands to shrink them down and combine Parquet files and minimize the size of your log entries across all these file types. Read about it. There's a lot of details about it out there. A lot has been written on this topic. I don't need to really introduce it here, but there are ways to optimize and compress and improve what happens to your data when you write to it constantly. So Parquet versus Delta Lake. People are always going to ask, which do I use? Which do I prefer? Why would I do one over the other? Parquet is great for data that is not updated often. Maybe you have the classic daily, weekly, monthly data load, where once a day you go in and dump a mountain of data and then you're done. Parquet is great for scenarios where you don't care about ACID, where you don't care about concurrency, where if I go in there and read the data, there's no chance that someone else is going to be writing to it at the same time and mucking up what I read. And you don't need history. The history is in your data pot. Maybe your history is already in your data already. You don't need further history or time traveling or versioning or whatever. So Parquet is great for that. In many ways, Parquet is kind of like what Columnstore Indexes gives you to a great extent. Delta Lake is when you need transactional compliance. You want ACID transactions. You want people who are going to be in there all the time to get valid data points. You want the ability to time travel, you want the ability to version. You have a lot of concurrency. So people are writing very often and reading very often concurrently. Delta Lake provides that. You can take data in one and convert it to the other. You can go from Parquet to Delta Lake if you want to. It's not obscenely hard. You can go from Delta Lake back to Parquet. You can convert between formats. I wouldn't call it simple, but it's not too hard. It's a well-documented process you can follow and get what you want out of it. Just keep in mind Delta Lake costs more. Having all that stuff to give you all of that compliance for time travel, versioning, ACID, and all that costs something. It's not free. Parquet files give you V-order optimization. This is available in Delta Lake and places that use things like Direct Lake, Azure Lakehouse, and so on, where this is just like Vertipaq optimization. It's the exact same idea, where it takes within each Parquet file, within each row group, it reorders upon compression all the rows to be in optimal order for maximum compression efficiency. Think of it as just like Vertipaq optimization. It even has a V in case you need that. They still remain open source and Parquet format compliant, despite its proprietary algorithm, because all it's changing is the order of the rows. It's enabled by default in many modern warehousing solutions, data solutions. Z-order optimization is where data is co-located in Delta Lake files. This is basically meant to be used as a way to pseudo-order the data within all of your transaction log files. If you filter very often by something or multiple somethings, you can create multiple optimizations. It's kind of like indexing. I'll say it's kind of like indexing with a lot of leeway here. But it's a way to get additional optimizations in a very active Delta Lake. Look about it, read about it. It's very interesting. What about proprietary stuff? You have data stored in other places besides SQL Server or Parquet files. The answer is, if they store data in a column-wise format, even if it's proprietary, you have no idea how it's stored or have minimal ideas, everything we talked about today probably applies to some extent. They probably have Columnstore in some way with encoding, compression, co-location, copying, indexing, row order optimization, Delta Lake structures, metadata analytics, and so on and so forth. It's all going to probably be there in some way, or else it can't be fast. It just can't be. So if you have data in Snowflake or Tableau or somewhere else, you have no idea how it's stored, consider optimizations that help analytic data storage, like these. Number one, avoid updates. Updates are expensive. They create lots of logging, take a long time to make compliant with ACID. They're just expensive. Keep data in order. Load data in order, maintain order the best you can. If your data gets way out of order due to stuff, maintenance, whatever, releases, consider reloading it all or reordering it all. Take it all from here, lift and shift it in order over here. In SQL Server, order to Columnstore is cool, but not quite production worthy yet. Getting there, but test though if you're going to use it. And again, you can look at the metadata for all of these storage formats, understand and fine tune when needed. So these are best practices. Use them wherever you can, no matter where you're storing analytic data, because it'll probably help you regardless of how it's stored. You can partition data, separating old from new. You can normalize giant data chunks, binary data strings, especially when cardinality is high. So a dictionary is more efficient. You can query only the columns that are needed. It's common advice, right? And if bulk insert functionality is available, use it. Insert more rows rather than less rows. Batching in transactional world makes sense. Batching in analytic world makes no sense. Insert all your stuff at one time. It'll be faster, I promise. Whew. That was a lot of information. I put it all in there really to focus on the fact that things repeat and get similar. If you know how analytic data is stored in general, you can improve data loading and analytic performance for all these different platforms and how they work, because many analytic storage engines have the same or similar architectures. Pick the best tool for the job, though, depending on whether your data is transactional, analytic, or mixed workload. And keep in mind there's a benefit to open source tools. If you're not sure your data is going to go, pick an open source tool. But if you're already using a certain tool, feel free to keep using it. That's very convenient. So with that, I'm going to open up to questions. I talked for a full hour. I don't think I've breathed yet. I will breathe now. Feel free if you have questions. I will post the slides as soon as this is over for you to have. If you have questions, feel free to send them to me or ask them right now. I am ready for questions, comments, feedback, a need for relief.
What an amazing session, I would say, Edward. Pretty good. Made fantastic. I'm still trying to unpack all the stuff on my brain, so it's just too much, and flush it out to disk. But that was amazing. Great information for sure.
Thank you. I do see a question here about taking into account the ordering of data in Parquet files. Typically, when you create your data in whatever Parquet file system it's in, it will order the data in the order that it comes in. If you have 100 Parquet files worth of data and you begin inserting the data into there, it'll just go in the order that you put it in. So if you put the data in order over the course of time or course of data or whatever, it'll automatically kind of be in order by the time dimension. But you want to keep that in mind, though. If you're inserting your data into your Parquet files, it's all out of order, it's going to read and compress about as well as misordered data would read and order. So you may not have to do anything, but just kind of keep in mind what your most common filter predicates are. Again, date times are very, very common. If you're not sure what to order by, just order by your time dimension and call it a day. I think for almost every Columnstore index I've ever created, almost every set of Parquet files, Delta Lake files, everything I've ever created, time has been easy. And the rare scenarios where I need more, you can use z-order optimization to get pseudo non-clustered indexes, or in the Columnstore world, you can use non-clustered Columnstore indexes on top of Columnstore, or you can use non-clustered Columnstore on RowStore to get your kind of real-time operational analytics. There's caveats to all those things. If I had another hour, I'd talk about them, but I don't. But there's more reading out there. Feel free to look me up. I have articles and presentations on Columnstore that go into deeper dives into details of it. I'm going to have similar ones on Parquet and Delta Lake and other things in the future. So you'll hear from me again, whether you want to or not. Any other questions or comments or anything else for me to dive into with all of the remaining time? If you think of anything, feel free to contact me. I'm sure that playing the YouTube video of this on 0.5 speed might help, as often is the case. How does this work in Fabric? And the answer is, if you're storing your data in Fabric and you're using Delta Lake or storing it in Parquet, everything I said here applies. And generally speaking, Fabric will use these formats. And so the beauty is that it's storing your data like this already. You're getting all of these benefits already. You can look into the details of it, of course. All of those formats are readable. If I was doing demos, we could dive into the demos and look at the metadata and the file formats and the file contents and the details of what's in your Columnstore index. I could look at the metadata in dynamic management views in SQL Server, or I can go into DBCC page and just get crazy and do memory dumps. But we're not going to do that today. But you could, though. So the answer to Fabric will give you this format. Just check and make sure. But odds are very good you'll be storing it in Parquet files and in Delta Lake, and that's what you want. That's exactly where you want. You want maximum compression, and those will give you maximum compression plus portability, which is kind of cool. Where can they see today's recording? Question for you.
That was a great session, and thank you so much for jumping in, and just it was truly mind melting, brain melting. A lot of information, a lot of useful information. Pretty much because you're going to be able to use these columnar storages across the board. I think GCS, AWS, and Azure to have the full-fledged capabilities, especially with Fabric that is coming up now with the Parquet and One Lake. So it's going to be amazing to have this background to understand how does it work. I think that's pretty much it. Thank you so much, Edward, for bringing this amazing presentation. We're going to have other, as Wander said, we're going to have other sessions coming up. So just stay up on the schedule, check it out. And if you have any questions, just drop us a message. Thank you so much again, everyone, and see you soon.
Thanks for having me. Have a great day, everyone.
Likewise. Bye-bye.